Hi, my name is Gabriel Kenrack. I'm 8 years old and I'm a third grader at the Fineman School in Rockville, Maryland. I'm going to talk to you today about repetitive patterns in the Juggler Sequence. I'd like to start with a short introduction to the Juggler Sequence for anyone who hasn't heard it before. A Juggler Sequence is an integer sequence, like the better known co-op sequence, so that where you start with an integer greater than 0, and to get the next term you either use the square root if it's an even number, or take the square root and cube the result if it's an odd number. Then you use the floor function to get it back to an integer. To make the full sequence, repeat this process until it hopefully converges to 1. We've computed all the sequences up to 1 million, and they all converge to 1, but there's no proof for all starting positive integers. It's also interesting to look at the longest sequences and the highest numbers in each sequence. Using Mathematica, made a graph plot of the first 24 Juggler sequences. The vertices are color-coded, so the higher numbers are lighter than lower numbers. Brown edges are from juggling odd numbers, and blue edges are from juggling even numbers. Notice that all of the edges near 2 are blue. It seems that small odd numbers have relatively long change, and in fact, you have to go 3 steps away from 2. Excluding 1, before you get to a brown edge. You can also see that there's lots of numbers going into 6 compared to 4 and 8, and there's a lot more ranging on the 6 side. We'll talk more about this in a minute. What we're trying to prove is they're all x. There's a finite number k, that's that if you compose the Juggler function, k times the value of that composition will be equal to 1. I hope you can use repetitive subsequences to make that general proof. It helps that every time a number appears in a sequence, the rest of the sequence finishes in the same way. I'm interested in subsequences that show up in a lot of Juggler sequences. For example, the sequence 11, 36, 61 and shows up in almost half of Juggler sequences up to 1 million. This is a plot of the fraction of sequences a given number appears in as a function of the total number of sequences you compute. Notice that the shape of the line for 11, 6, and 5 are almost the same, but not identical, which we expect because 5 goes to 11, and 11 goes to 36, and then 6. 4 and 6 need to trade, because when 6 goes down, 4 goes up, and vice versa. Not exactly, because you have to take 8 into account, which kind of squiggles out on itself. If you look at the inverse of the Juggler function, the only way to get to 1 is through 2, and the only way to get to 2 is through 4, 6, or 8. 4, 6, and 8 have 5, 7, and 9 predecessors respectively. Because of this, we expect that the ratio of subsequences that go through 4, 6, or 8 would be 5 to 7 to 9. However, at least in the first million sequences, this isn't the case. 6 shows up in 60%, while 4 and 8 are only in 25 and 15% respectively. We don't yet know why this is. Also using the inverse function, we can see that if there are any Juggler sequences which don't converge, it will be an infinite number, because every number in the sequence will have many predecessors. The base strategy for finding a proof is to try and figure out the properties of a number whose Juggler sequence doesn't converge. There are two scenarios where that would happen. Either a Juggler sequence that diverges or a sequence that loops. There are no trivial loops, which means that any loop would have to be very complicated. As a person, there can't be a trivial loop in the handout, which is in the gift exchange. If we can show that there's a number whose sequence doesn't converge, can't exist, then we've got a general proof.
30 seconds.
That's about all I can fit in 5 minutes, but I have some more work that I've done on this, which is also in the handout. I really want to thank Wolfram Research for giving me access to Mathematica. I could work on this, and also Bill Baxter for helping me figure out how to use Mathematica to make all my plots. Thank you for listening. Are there any questions?